Hi there, and welcome to my presentation. My work is about Modelica-based simulation of electromagnetic transients using Dynaωo current status and perspectives. This is the outline of the presentation. First, we have an introduction on Modelica and Dynaωo. Here we have some examples how to model with Modelica. Then we go to the simulation results. We have three cases: capacitor bank, switching of transmission line, and nonlinear circuits of surge arrestor. And at the end, we wind up the presentation with conclusion. This is introduction. First, we would like to answer the question, what is Modelica and what distinguishes it from other languages? As a definition provided by the Modelica Association, Modelica is a declarative, object-oriented, equation-based language specifically designed for cyber-physical simulation. In Modelica, in contrary to the imperative classical languages such as MATLAB and Fortran, there is no need to declare the codes as assignments and in order of executions. The focus of Modelica is on equations instead of solutions. The variables are intrinsically time dependent. I try to explain these concepts by examples in the next slides. In Modelica, the models are totally decoupled from the solver, and we have the ability to select a variety of solvers such as fixed step variable solvers, including variable order solvers, to simulate our models. There are different IDEs for compiling the codes of Modelica, such as OpenModelica, Dynaωo, and System Modeler. This is an example to show how we can model a simple RLC circuit in Modelica. In the left side, we see the schematic of series RLC circuit with these equations. In the right side, we see the Modelica codes. First, we define the parameters of the model. Then we define the variables. And at the end, we define the equations of the model. I would like to draw your attention to the point that we just need to declare the equations, and the order of equations is not important. This is the second example to show the abilities of the Modelica. This is Chua circuit, a chaotic system with nonlinearities. Here, this is the schematic of Chua circuit drawn and sketched in OpenModelica. We have capacitors. In Modelica, we can draw an illustrated icon for each component model. We can define the codes and package it. The connection between components is very easy. I have to draw your attention that this is the physical connection. It means that there is no data flow between them, and this is a causal connection. In Modelica, we have GUI for entering the parameters of the model. You can see here for the Chua diode, sorry. In this example, we have shown some properties of the Modelica, such as object orientation and equation based. This is the third example to show the electronic device applications in Modelica. This is a thyristor demonstration. This is the schematic of voltage source in series connection with thyristor and RL load. This is the voltage current characteristic of thyristor. Here we can see the GUI of parameters, practical parameters of the thyristor. This figure shows the impulse current for firing the thyristor. And in below figure, we can see the graph of sinusoidal voltage in blue curve, and the red curve depicts the cathode voltage of thyristor. Now the question posed here is why we have to use Modelica. In the previous examples, we have tried to justify the reasons using for Modelica in EMT simulations. For example, in Modelica, we have physical connection of component models. In Modelica, we can easily express the mathematical representation of dynamic behavior of system in the form of differential algebraic equations and ordinary differential equations. In Modelica, there is no limitation for incorporation of the nonlinear and power electronic components with power electric elements. We have simultaneous solution of entire circuit, including the control and power circuits in Modelica. Modelica language is a user-friendly and well-documented language. We can benefit from the GUIs and illustrative icons in Modelica. Modelica is suitable for simulation of larger scale networks, and also Modelica language is more efficient than similar languages such as Simescape. Modelica is fully compatible with FMI standard, which enables us to have a model exchange and co-simulation in Modelica. We know that the main drawback of EMT simulations in Modelica, specifically for larger scale networks and circuits, is efficiency. EMT simulation using pure Modelica is not as efficient as EMT simulators such as EMTP. The main objective of this paper is to use Dynaωo for EMT simulations. Dynaωo is a open source hybrid Modelica and C++ solution developed by RTE initially for phasor domain simulations. In the right side, we can see the structure of Modelica. We have Modelica models in the first level. Then the models are compiled in C++. Together with other C++ models, we construct the global models. We have two solvers, modified IDA and modified backward Euler. We benefit from the open source libraries such as the Sundial. It's mentioned that we use the pre-compiled libraries to reduce the compilation time of Modelica models. We have upgraded the IDA solver for EMT simulations. Also, a delay function has been developed to model CP lines for EMT purposes. In the next slides, we will speak about the examples of EMT simulations using the Dynaωo. It must be mentioned that the documentation of the Dynaωo suite is available in this website. This is simulation results and numeric analysis. We have simulated each case using 3 simulators, Dynaωo, Open Modelica, and EMTP. In the first case, we have capacitor bank switching. This is the schematic of two-step back-to-back capacitor bank sketched in Open Modelica. This is the opening and closing times of CB1 and CB2. Here, this is the properties and parameters of the solvers in Dynaωo and EMTP. In the right side, we can see the voltage waveform across C1. We can see both high frequency and low frequency transients. In all cases, we can see an excellent agreement between results obtained by Dynaωo and EMTP. This slide shows numerical analysis for the first case. This table shows the CPU time obtained from the simulations in Dynaωo, Open Modelica, and EMTP. I draw your attention to the number of time steps for each solvers. We see that the number of time steps in Dynaωo is at twice the EMTP. In the right side, we can see the voltage waveforms across C1 for different IDA solver tolerances for 1 - 6, 1 - 5, and 1 - 4. We see that when the tolerance increases, the number of time steps increases as well. In this table, we see the CPU time required for simulations for different tolerances. As we can see, when we increase the tolerance, the CPU time increases as well. This is the second case, which is about switching of transmission line. The goal of this case study is accuracy validation of the delay function developed in Dynaωo and stability of the solver over discontinuity imposed by several state events. This is the schematic of a case study. We have a network equivalent. We have 2 transmission lines modeled by CP models. We have faults. This transmission line TLM2 is disconnected after fault and reconnected after removing the fault at these times. Here we can see the details and parameters of the solvers for Dynaωo and EMTP. Here we can see the voltage curves at the point M here, at the M end of the transmission line TLM2, before fault, during fault, and after fault. Here we can see the close-up views on initialization, and at this time we can see that in all cases we have an excellent agreement between results obtained by Dynaωo and EMTP. This slide shows the current graphs at the M end of the TLM2 obtained by Dynaωo and EMTP for phase A, B, and C. Here we can see the close-up views of these two intervals. We can see an excellent agreement between the results. In the right side, we can see the performance comparison between simulators Dynaωo, Open Modelica, and EMTP. The Dynaωo performance is close to the Open Modelica, but better, but has a great gap with EMTP. I would like to draw your attention to the number of time steps in Dynaωo, which is twice EMTP for this simulation. Delay function needs to be optimized for variable step solver to improve the efficiency in Dynaωo. This is the third case study, which is about the simulation of nonlinear circuit of surge arrestor. The circuit has been introduced by IEEE for validation and simulation of the surge arrestors. Surge arrestors in Dynaωo has been modeled using these equations. This is the parameters and properties of solvers in Dynaωo and EMTP. In the right side, we can see the residual voltage and discharge current for Zn2. We can see that the results obtained by the EMTP and Dynaωo are superimposed. In below, we can see the nonlinear resistance of Zn2 obtained by Dynaωo and EMTP. We can see an excellent agreement between these two solvers as well here. It should be mentioned that in both solvers we have used the iterative solutions. This table shows the performance comparison in Dynaωo, Open Modelica, and EMTP. We can see the CPU times for each solvers are close together. I draw your attention to the number of time points, which in Dynaωo is about 31,000 and in EMTP is 30,000. As conclusions of this research, we saw that Modelica is a powerful language for EMC simulations. Models are easily coded in Modelica. It's easy to share and understand the codes of Modelica. Dynaωo approach improves the runtime of EMT type simulations compared with pure Modelica tools such as Open Modelica. Highly nonlinear elements such as surge arrestors have been successfully tested with Dynaωo. Modified IDO solver has no numerical noise during discontinuity treatments. And as a future work, we would like to concentrate on the simulation of larger systems in Dynaωo. Thanks for your attention.